All right, so thank you for joining the channel. So let's go ahead and get started. So again, today we're going to look at our dependent voltage sources. So here I have an example where we have what's a classic mesh equation or three loop type of problem, where if you look at it carefully, we have our dependent voltage source right over here, and it's has the -3 V naught, and over here you have where it's dependent on. So in other words, dependent on the 3 ohm resistor. And again, what this means that this is like a factor of 3 that's affecting the voltage source. In addition to that, the current of this branch of the resistor. All right, so that's what we're trying to focus on. And again, I'm going to produce a video using LT splice of this as well to give you the hang of it. So as we look at this problem, feel free to take a screen grab so you have this actual image. And we're going to go ahead and start. So how do we start this problem again? Is that because we have 3 loops, we can go ahead and try to use our 3 loops or 3 mesh approach. And the idea is that I went ahead and labeled it. We're going to label our mesh currents of I1, I2, and I3. I'm going to go around each one and write a loop equation for each. So in other words, I'm going to start on the corner like I've done in previous videos. I gotta say this is A, B, C, and D. I'm going to write the KVL equation for each loop. In other words, the voltage, all the voltages in our loop should equals to 0 based on Kirchoff's explanation. So if we do that and we have our loop 1, the idea again is that we're going to write that loop 1 equation. And if I start on the corner, listed as -25 volts, then the next component that I see is a resistor. Because I am in loop 1, is going to be I1 minus I2 plus, and then again this is going to be 5 ohms, and I'm still in loop 1, so it'll be I1 minus I3 plus 10 volts equals 0. And if you haven't seen the previous videos, the idea is that because I go clockwise, the notation for all of my resistors as I approach it, well, my current source will always enter in the positive end of my components. Okay, so it's read as positive, negatives for each of my resistors. So at this point, it's not too bad. The idea is that we're going to simplify this equation and try to solve. If you've noticed in the previous videos, what do? I'm just going to simplify all of my equations to simplify as best as I can. So here we go. And we're going to do it relatively fast, I hope. And of course, the hard part is to ensure that I don't make too many algebraic mistakes, which can tend to happen. Okay, so now that I've done that, I can reduce this entire loop 1 to just one equation. See if I don't make any algebra mistakes. Here we go. Okay, so now that I reduced that to one equation, that wasn't so bad because again, it's loop 1. And why is it not so bad? Because in loop 1 and loop 1 only, you'll notice that there is no dependent sources. So everything is independent. So it makes our lives, at least in my opinion, a little bit easy. So now we're going to get to loop 2, where it's going to get a little bit more challenging, right? So loop 2, here I already have the image there for us for loop 2. And you notice now that you have a dependent voltage source in there. I'm going to highlight it for you again. So here it is, and it's illustrated as -3V. So how do we handle that? So because we are in loop 2, right, it's going to be read as -3V0. And the question you might have is, why do I immediately go to -3V0? Again, this here means voltage. And how do I know it means voltage? Because there's a minus and a positive terminal on my dependent source. Because your dependent source has a polarity on it that's treated like a voltage source, but at an arrow on it, it'll be treated like a dependent current source. Really important to keep that in mind. So my next component is a resistor. And that resistor, again, will also have, because I'm going clockwise notation, all my resistors are going to take the notation of a positive sign. the current entering that branch. So I can read it relatively easy. So it's going to be 14 times it by I2 plus I'm in loop 2, so I'm I2 and I'm going opposed. So I2 minus I3. Finally, it's going to be plus 2, still in loop 2, I2 minus I1. All of that equals to 0. Okay, so that is how we do that, but we made one mistake here. So at least I'm trying to show you where mistakes can happen, because it's written as minus 3 volts, but the sign convention here, I'm reading it when I go clockwise and negative. This is actually going to be read as minus 3V naught. Okay, so it's really important that you understand that. And why, again, is because of the sign convention here with my polarity. If the problem was written this way, so say that on our problem it was actually a dependent source, but the dependent source had a positive first and a negative first, but it's still read as minus 3V0 or V naught, then it's going to be read as minus 3V0 as I go around it clockwise. Or if it's written as just 5V naught, then it'd be positive 5V naught. So because the convention of the sign, right, takes precedence always with voltage sources, dependent or independent, you have to remember to include that there. Okay, so keep that in mind when you do those problems. Okay, so now that we've gotten that part out of the way, and hopefully this makes sense about the convention of the sign for voltage sources, either if the independent or dependent takes precedence, then you have to make sure that you include that sign here. It's very rare to see this minus, by the way, how you see it written here, but it is what it is. We're just going to go ahead and continue with the problem as we see it. So a minus and a negative make this a positive 3V naught. Then I'm going to distribute these out. So this, of course, turns into 3I2 minus 3I3. This one here is 2I2 minus 2I1. So I have several I2, right? So I'm going to be left with, and I only have one I1. So algebraically, what I'm left with, I'm going to have to be left with minus 2I1. And this turns into plus okay, let me put this all together so you can see it. Is what we're left with. Okay. Now certainly you can move the 3V naught to the other side, but I'll show you why that may or may not make a big difference as we go through this. So again, this is what we're left with our second equation. We do this one more time for the third loop, and we're almost there. So let me just go ahead and copy this as well. So if I copy this and I paste it again. So the third loop, I'm going to look at this over here. So over here, it's minus positive, but then I take on the positive negative. Notice on this particular problem, they tell you this to be positive negative, by the way. Maybe that's going to be of use in a little bit. And then, of course, positive negative again. So when I write this equation, right, I'm going to go through this as I did before. I'm going to start over here, the far left corner, and I go around this on the dots that I just referenced right here on the screen. So we read as minus 10 volts. Plus, I'm in loop 3, so it's going to be 5, I3 minus I1, plus, right, 3, I'm in loop 3 still, I3 minus I2, plus 1 I3 equals 0. So if I, of course, simplify this, so we left with the 5I3 minus 5I1 plus 3I3 minus 3I2 plus 1I3 equals to 10 volts. Okay, so now that I've done that, let's make sure we don't make any algebra mistakes. So here are all of our I3 terms, one I1 term, one I2 term. What the minus 5I1 minus 3I2. What is that? That gives us 2. Make sure I'm getting my algebra right here. So get back our 9I3, okay? Okay, so just like that, we have our 3 equations, okay? So if we, and again, this is hopefully going to feel like it's automatic because you've seen something like this or gone through it. A previous video of mine, you should hopefully have it condensed in this form. So now we have this problem. We have to figure out our big issue. And our big issue is that we're going to have 3 equations of this problem and 4 unknowns, right? That doesn't seem plausible or something easy that we can solve for. So what that means is that we have to search for what is our constraint on this problem. So identifying this constraint takes a little bit of time and practice, but hopefully after this video, this make a lot more sense. And again, this is just a gain effect, right? It's a gain of -3, right? Sometimes threefold, this one's minus threefold. So that's the gain that's caused by this dependent source. And what is this dependent voltage source depending on? Where it's depending on this V0 over here. So what we can see from this problem is that we've illustrated that if we go clockwise notation everywhere, right? So if I go clockwise for I1, if I go clockwise for I3, and then I go clockwise for I2, we get something pretty interesting as far as the behavior of the V0. And if we look at V0, which is this piece over here, what it looks like as far as it's concerned, it's going to look like you have I2 going this way and I3 going that way. Okay, so we can define I3 and I2 to be opposed each other. This is what you get here. So some of you guys are asking, says, wait a minute, why do you not use I2 minus I3? How do you know with confidence that it must be I3 minus I2? And that's a really important question. So the rationale of why it must be I3, because on the problem, we're given the polarity here to be plus here. The polarity on the left side, on the right side to be minus. So remember what the rule was, that if we're going to use clockwise notation to solve these problems, our current source will always enter the positive terminal. So if the current's entering the positive terminal, it is registered as a positive. Okay, so think about that for a moment. So that's how we can say it with confidence that this is the constraint. It's going to be 3I3 minus I2. All right. It can't be the other way because again, then you know the convention of signs would have to be the opposite way, which means that I2 is dominating, but it's clearly saying that the plus sign is over here. And the only way to get the plus sign in my convention going clockwise is that I3 must be entering into this positive terminal. Hence why it's I3 minus I2. All right. A little bit of practice will start to click on how this is for sure the way. All right. So what we end up with is that we're going to get 3 equations and 4 knowns as the big picture. So let me go ahead and copy these for you so you can see it all at once. So this is my loop 3 equation. So I'm going to copy and paste that and put them all here for you. And again, I recommend when you're just getting started with this stuff to just kindly make sure that you try to stay neater than I. And when you do that, in addition to that, try to keep it as organized with explanations as possible. As what I try to do as well is that when I'm working on this stuff is I try to keep in mind all of the strategies and all of the steps that I'm working on. Okay. All right. So hopefully I copy and paste that right. Did I do that? Yes, it looks good. So here are my 3 equations. I'm going to clean this up slightly for you. Don't need the color anymore. Okay, so the catch now that you can see here is that, how do I know it's 3 equations? Well, it's equation 1, 2, and 3, but where's the 4th unknown? And the 4th unknown is this one over here, the 3 V naught, because I1 is an unknown, I2 is unknown, I3 is unknown, but the V naught is unknown. But is it really? And the answer is yes and no, right? Because as long as you keep in mind the constraint, this constraint piece here, you can now get this back to being a 3 equations and 3 unknowns, and then you're quasi done with these problems. So the dependent problems look kind of rough and scary at first glance, but in reality, you have to think about it as some sort of game. So a multiplying effect. So if you raise your volume knob or something, and it goes up exponentially by 3x as an example of what a dependent source would do if it's attached to a certain portion of the resistor. And of course, if you read on your textbooks, you'll learn that has to do with a lot of other things like amplifiers, how signals are amplifiers. These dependent sources are great because they can take these type of phenomenons like op amps and reduce it to something simple that we can calculate with mathematics and solve for complicated problems more readily. And again, that comes with practice, and you'll come to understand that and appreciate it, hopefully, as we go through these series of videos. Okay, so now that we have that understanding, what we're going to do now is that we're going to try to clean this up, all right? And I should have moved the 3 V naught over to make it a little bit more ideal, but we'll just roll with it. This is technically how we should have actually left it. So in this case, we could also write this as 3i3 minus 3i2. Okay. So now we can replace this with minus 3 times it by 3i3 minus 3i2 and distribute that out. So you're going to be left with this entire thing goes to minus 9i3 and then positive 9i2. And certainly this will remain the same, so I can copy and paste that to make our lives a little bit easier. And now we're going to simplify this again by trying to put all of our like terms together, right? And hopefully this will be reasonably okay. So in other words, if I subtract the 9i2 from this side, from the right side, move it to left, and I add 9i3 from the right side and move it to left, we should be left with the following, right? It should be left with the minus 2i1 and minus 9, so this will make it positive 10i2. And I move the 3 over, and I should be left with plus 6i3, right? So I'm left with this finally to being our new equation, right, that handles the dependent source. And that's the name of the game, right, is to how do we handle this dependent source. So with all that, right, here is us to save a little bit of time, right? So I just copied and paste this piece over here, and I moved it down. So here was our original set of equations. We had 3 equations and 4 unknowns, and now we have 3 equations and some typos here, 3 unknowns, and let's write it all the way out for you so you can understand what I'm doing. And UNKS is my abbreviation for unknowns, and we're all set. Okay, so now that you have that, you have something that's way more straightforward to solve for. So we can take this equation and we can now use it by using determinants to solve for I1, I2, and I3. All right, so most of the heavy lifting of this problem that originally looked pretty complicated, it hopefully feels more comfortable now. And now if we put it into this determinant form, we can certainly solve this matrices. So what I do, again, please take a look at another one of my videos, but I took the 7, minus 2, minus 5, minus 2, 10, and minus 3, minus 5, 6, and 9, right? I put them in matrix form so I can solve for the determinants. Technique we've learned in our linear algebra type classes. And in order to do that, let's just do 1 or 2 of them together. I think we have time. So when we do that, we put the 7 externally. And then I'm going to create a 2 by 2 matrix out of this. This is the technique that I like to use. It's a little bit more convenient for me, but choose. There's two theories on two methods to do this. So you choose what you feel comfortable with. And here I am just creating the matrix to solve for my determinant. So big D for determinant. Okay, so now I'm going to cross multiply. And what am I cross multiplying? Here and here. And we're going to go ahead and solve. So I'll write it all out so you can see how I'm doing this. And then after that, you should be able to solve for the rest on your own. All right, so now we're ready to solve, right? And again, this is hopefully just algebra at this point. So I'm going to go ahead and do it, and you should either pause, try this out yourself, and see what you get. And hopefully it matches what I have here on the screen. Okay, so far I think I'm looking pretty okay with this. So I'm gonna use a little calculator here as well to make sure I'm plugging this stuff away, but please work on this with me, right? So 90 minus 18 times it by 7 goes back 756. So you have minus 18 minus 30 times it by 2. So this should be minus 24. And then finally you have here 56 times 5, right? And you get back a minus 280. Okay, so all of that, if you punch all that in, all that should give us back, let's see here. So all of that should give us back 500. And that equals to our determinant. All right. So now that we have that, it makes it so much easier to solve I1, I2, and I3. So in order to do that, this is what we're going to do. So first, I actually put the equations here so you can see them all simultaneously. It might be a little bit easier to see. Okay, so now we have, in order to solve for I1, okay, so this is your I1 term here, you're going to put in the 15, 0, 10, our solutions to each equation into that first row. If you want to solve for I2, you're going to use the same determinant and replace it with 15, 0, 10 over here. And again, this is all Cramer's rules. You can go ahead and look about Cramer's rules to do that. I should also have a video on Cramer's rule as well. So 15, 0, and 10. And we're going to use that all of it over to determinant D to solve for I1, I2, and I3, right? And that is how you set it up. So if you can set it up this far, you're in fantastic shape. I'll do one, and then I'll pause the video so you can see that and give you a chance to try this out. And then we can do I2 and I3. And once you have the feel for it, it's not so bad. So let me just go ahead and take the lead for I1 for you. And feel free to pause and try this on your own to get sure you get the practice down. It works out well if you get a chance to work on this, right? Okay, so this is how you set up to solve for I1, right? And the rest is hopefully just cross multiplication solving. All right, so that's the quick setup for this. The rest is hopefully algebra. So we're gonna just, if you quickly go through this with me, you should do some basic algebra, I hope, right? So negative 100 times by minus 5 gives us back 500. Minus 60 minus 2 times it by a negative. So I just leave it as negative times a negative is a positive, then a negative, so you have minus 120 here. And the first term, 90 plus 90 minus 118 gives me back 108. 108 times it by 15. So you get back 1620. Okay. And all of that, let's see here, 1620 minus 120 plus 500 gives me back 2000. Okay. So in order to solve for I1, I1 is going to equals to 2000 over D, where D equals to 500. So therefore I1 equals to 500 times 4 gives me back 2000 again, so you get back 4 amps. Okay, so that's how much current is going through loop 1. That's the current through loop 1. So excellent job if you were able to get that. So let's quickly try to set up I2. So I2 is the same thing that we did before, so we're going to just practice for speed, and hopefully in no time when you work on this, or if you take an exam on this, you'll feel a little bit more confident on how to do this. Okay, so now we set up our form to solve for I2, right? And then just again, cross multiplication again. So let's see if I can do this relatively fast. Okay. All right, so now we're able to do that. You know, the rest is just algebra. So let's see if we can quickly do this and see what we get. So we get back minus 30 over here, minus, minus 18, all that times it by 15. This one, of course, just minus 20 times by minus 5. Okay. So this one gives us 100. Sorry. This term gives us 100 over here. This one gives us minus 180. So we get back that this entire thing sums out to be minus 500. So therefore I2 is going to equals to minus 500 over D, where it's minus 500 over 500, and I2 equals to minus 1 amp. Okay, it's always nice when these problems solutions work out nice and crisp and beautiful, like whole numbers, but that's not always the case, and then you get nervous, right, when things are not perfect. But again, we got lucky with this one. And finally, with this one here, we'll have I3. Then I3, then you should be all set. So for I3, it's the same logic. So let's go ahead and do this. So it's 7. Okay. So now that we went ahead and set that one up, it's not so bad as well. So 10 times 10 gives me 100. 100 and minus 3 times 0 is 0. So this term here just comes up to be 700. So this one's minus 2 times 10 is minus 20. Minus 20 times it by minus 0, because minus 5 times 0 is 0, of course. This is what we get here. So let's see, it gives us back minus 40, right? And then the final term is going to be 2, going too fast now, minus 2 times by minus 3, minus 5 times it by 10, all that multiplied by 15. So what is this? Right? So what is that? 40. So get back 840 for this last piece. So all of this, so 700 plus 840, and then minus 40, so that brings us back to 1500. So I3 equals to 1500 over 500, which equals to 3 amps. All right, just like that. Congrats, you made it through, right? What possibly would felt like a little bit complicated, I try to put a, hopefully I'm going to cover easy problems with dependence, medium problems, and also hard problems as well. If you have any problems you're interested in, kindly share it to me in the chat window. That'll always be great. And ideally, what I'm trying to do is provide you with an opportunity to solve any of these type of problems, okay? And without too much issues, and make it convenient, simple, nice and easy to use. So just put this right back for you to see the big picture again. And here's the big picture. I'll try to get a better image. So here's the big picture finally. We're here. So that means that we can solve for the currents everywhere and the voltages everywhere for this particular problem, which is really, really powerful. All right, 4, 1, 3. So let me put this down here so I don't forget. So we're able to solve for it. So we had 4, 1, and 3 amps for our solutions. And all of them should give us back KVL equals to 0, right? Which means that every mesh loop should mathematically come back to be 0. We can do a quick test so we can see how paranoid or crazy we are. So if we look at loop 1 as our check, right? So then we can read this as minus 25, and here are my corners. Always start at the bottom left-hand corner, I go around. So we expect this is to be minus 25 plus 2, and I call this one I1. What did I call the top one? I2, I believe. Just triple check for one quick second. Yeah, the top one is node 2. All right. So, and then the final one is going to be plus 5 times it by I1 minus I3. Ran out of real estate. Oops. Again, this is part of our check. Plus 10 volts should hopefully equals to 0, right? As a check to see if we did it right. So if we now substitute our values of I1 and I2, so let's go ahead and do that. So it's going to be 4 minus 1 amp, right? And this piece is going to be substituted with 4 minus 3. Okay, sorry, I'm doing all this live for fun. And this time minus 25 and positive 10 gives me back minus 15 volts. I'm trying to condense this. So here's the problem. So let's see, we get back 3 times it by 2 plus 5 times it by 1 minus 15 volts equals to 0. So get back 6. Did I do an algebra mistake here? So I see I did another error. So my error here is just I transcribed incorrectly. So remember I had minus 1 over here. I somehow put a positive 1 here, which is not very clever. We'll go ahead and fix that because I need something to look right. So it's actually 4 and then I2. Let's clarify this for you. So we minus 1, right? And then I think this will work now. Okay, so let's see here. So it becomes 4 minus 1 gives us back 5. Right, so this turns out to be, I knew something looked weird, but it happens when you're transcribing too quickly. So you get back 10 volts plus 5 volts plus the minus 15, right, equals to 0. So therefore, it all checks out. Okay, it's which is great. So that means we proved KVL for that particular loop, which means that we should technically work for the other loops as well. You know what? So what we can do, if we look at loop number 2, for example, this time we can substitute, we can do loop 2 next because it makes more sense in order to solve for the final one. So let me go ahead and copy and paste that for you. So the loop 2 equation is over here. You just copy all the equations so I can see it. Okay, so this is my loop 2 equation to save some time and energy. Okay, so when you have the loop 2 equation now, it should also work. So it's minus 2 times it by 4, and this one's plus 10 times it by minus 1, right? Plus 6 times it by 3 amps, right? Equals, so let's see, minus 8 plus minus 10 plus positive 18 equals to 0 as well. So we get back 0 equals to 0. So that also proves the KCL. So definitely a matrix works. We don't have to go too insane for it. And of course, we also know that we substitute in for V0 to show that this works as well. All right, so it's a quick check. So check that out yourself. This is just a transcribing error, not a math error. The transcribing error was done, I went too quickly with the copy and paste, but you'll take your time for it. And that is it, right? So this is a quick way to go over this, give you a chance to do this problem, see the solutions, and hopefully feel more comfortable with something like this. But if you like the video, kindly subscribe, thumbs it up, and I'll continue making some more. And I will also have this video for you in LT Spice to show you how the simulation looks like with their software. All right, it's been great.